Welcome back to ECE 320A. We're working through some review problems for exam number 4. This is problem number 3 from an earlier exam from fall of 2015. This one is asking us about the pole zero pattern, or to sketch the pole zero pattern in the complex plane and then determine an angle that's contributed or associated with one of the poles or zeros. So the first thing you want to do in these kinds of problems is actually factor the quadratics to make sure that those are either real roots or complex roots. In this case, you can factor the numerator. We have an s squared plus 2s plus 2, and you might be able to see that already by sort of completing the square, that you have an s plus 1 quantity squared, which gives you an s squared plus 2s plus 1, and you need one more to make up for the 2. So we now can see that we have complex zeros at minus 1 plus and minus j. The poles, let's see if we have any complex. Now dealing with the poles, we have 1 at s equal to minus 2. That one is already identified for us. Now we need to look at what results when we examine the roots of s squared plus 4s plus 3. And this one actually, if you're remembering all of your factoring skills, we can now see that, in fact, we have 2 real roots sitting inside that quadratic of s squared plus 4s plus 3. Now we're ready to sketch our pole zero pattern. We have zeros at minus 1 plus and minus j1, and we have poles at minus 2, minus 1, and minus 3. And you might want to label some of these locations on your plot. But that's all there is to it in terms of the pole zero pattern associated with this transfer function. Part B asks us to find or determine or compute the phase angle associated with the complex pole of h of s that is located at s equal to minus 2. And if we look, we don't have any complex poles, so I've actually had a typo here. We shouldn't even have that. We should say the phase angle associated with the, if we wanted to, we could say real pole, or we could just say, well, if it's real or complex, let's assume that it has a real part of s equal to minus 2. But once we've now figured out that there was a typo, now we want to know what's the angle that that pole at minus 2 produces when we're at omega equal to 0.5. And omega is now when we're marching or walking along the imaginary axis, and omega equal to 0.5 actually puts us right there. Whoops, I just erased my axis. Hopefully I haven't done too much more, but now that's right there at 0.5. So for part B, what we're really wanting to do, and you could bring in your protractor, I guess, if you wanted to, we now are over 2 and not up 1, but we're only up 1/2. Here's J 0.5, and we're now trying to find what's the angle from this pole location to that point. We want to know what's this angle. That's theta p, and because it's a pole, it's downstairs. So if we find this angle as, let's say, 15 degrees, then we would actually say the angle associated with that pole is minus 15 degrees. And this theta sub p is now going to be the angle that has, or the inverse tangent of that angle, or the argument of the inverse tangent, is its vertical distance is 0.5, its horizontal distance is 2. So if we do the inverse tangent of 0.5 over 2, then we find that this will actually be 14.04 degrees. And because it's a pole, we can assign that a negative angle. And so the angle associated with that pole at s equal to -2 at a value of j 0.5 would be computed this way. We have a vertical displacement of 1/2, a horizontal distance of 2, and because it's downstairs, it's a pole, it's going to have a negative angle. We're subtracting all of those phases that are associated with poles. If we wanted to know what's the angle associated with that pole at s equal to -2 when omega is equal to 2, now we simply have to walk up the j omega axis until we reach 2, and now you should be able to see that we're up 2 and over 2. That would be then an angle of 45 degrees, but because it's a pole, it's now at -45 degrees. And that's where the -45 degrees at the break frequency is coming from.